function, if you remember or not from previous lecture. So generally, we need to have independent and identically normally distributed errors, and this allowed us to estimate the parameters, because we can use the properties of normal distribution to say something about parameters in our model which we want to estimate. And then we need these standard assumptions. So, and then, yeah, here it's supposed to be the graph. So if we are talking about normally IID errors, then you can see the first graph, and you see that if we are thinking about observation from 0 to 100, then the error is kind of similar, and that's what we need to use the normal, yes, the properties of normal distribution. And then stochastic errors, it's then you have different variants, and then this means that the errors can be higher or lower for different observation. And you can see that, for example, here, the first 50 observations, we have low variance and then higher variance. So that means that we cannot use these observations together, because we have different variants, and then it's going to have different properties. And what is probably, yeah, the main purpose of having variance and knowing variance of our errors? What we want to estimate after then we get the estimation for our parameter. What is the next step we normally do? Some ideas? So we need to understand, can we trust to our estimation or not, so that if our estimation can be used, and that's why we are building inference interval, right? So have you discussed it? I guess yes, already. No? Okay. So then to build the inference interval, you need the variance of your errors. And then if you have different variants for different observation, you cannot build the correct inference interval. And that's about the second example. And then the third example is the autocorrelation. So then, for example, it's can be a problem for time series observation. Then your second observation depends on the result of first observation in terms of errors. So that if you take first observation, then your error in the second observation can be affected, for example. Yes, and then you have the similar problems. So that's why we need this assumption for OLS. And so that what what can happen if these assumptions are violated. So if we already talked a bit, so if we have heteroscedasticity, different variance for different observation. So then, we cannot tell that our estimator is efficient, and then we have problems with variance, and then we cannot build the inference interval and to test for significance. Yes, if we have autocorrelation, then we have a similar problem with inefficiency. And then we have problems with our test, so they then cannot tell much about our estimator, how it's good enough or not. Well, yeah, so that's if we are evaluating the assumption of normality, and that's one of the, all of them are main assumptions, but so the normal distribution is the main stuff which allowed us to say something about the estimation, because we know properties of the normal distribution, and then can say a lot of stuff. So build the inference interval, talk about significance, and so on. So then if you don't have the normal distribution, then we actually cannot say most of the standard things about OLS. And in econometrics, there can be used different distributions. So if you know some, for example, that errors are distributed according to different distributions, so then you can use it as well, but we're not going to talk about it today. And another relation is if we have outliers. So can you guess what is outlier? Yeah, for example, how you can describe the outlier observation. Yeah, extreme values. And for example, right. And normally we would like to throw it away from our analysis, because normally, one second. So in observation, it always can happen that for single person or a single observation can happen something unusual, and then the results, the result for this exact observation will be somewhere far away from the most of them. But if you will take it serious, it will affect your parameter, because if you observe something, for example, if you make a survey about your income and asking people on the street, and then among 1,000 persons, 999 answered you truthfully. And if you want to somehow build a correlation between age and income, you ask about age and income, and then only one person will say something like, I'm one 100 years old and my income is 0, or some opposite, that I'm 5 and my income is billions dollars, then yeah, in this case you can say that okay, you looks like 30, for example, and dressed not that well to earn billions of dollars, and throw out this observation from the beginning, but can be some different cases. Then you cannot just see that someone lies in survey or something like that. So you have to find these observations in your data and throw it away, because most probably they are not reliable. And we will talk a bit today how to do this. And let's move. Yeah, so that's there are some tests how you can test the just a second. Okay, so you can see different tests which can help you with identifying some violations if you have observation. And I guess you will study most of them during the econometrics courses later. We will discuss a bit, mention the test about outliers. And so, but if you need to test on different stuff, you can see some tests which you have seen here. For example, about heteroscedasticity, you can do the white test. It's so called because if you have ID errors, so it will looks like the white noise. And for autocorrelations, different tests, and non-normality, and so on. So then, do you have any questions by now? Okay, then we already mentioned that if something wrong with data, if we violating some assumptions, we are losing these nice properties about OLS. And so here we're going to discuss these outliers, so that if in our structure we can imagine this example with correlation between age and income. And if you ask people on the street, and then some guy told that he's 5 years old and earning billions of dollars, then we need somehow to identify it. Yes, and this will strongly affect our estimation. So that outlier is the observation which lies far away from another values, and we need to identify them and drop it out from our observation set. So then let's see how it looks like. Yeah, for example, here you can on the top graph you can see the example of observation. So the black dots are observations. Then the green line is the estimated OLS model without the outlier, and you can easily guess that this one is outlier. So that if you drop it out, you have the nice green model which better estimates and describe the data. But if you take it into account with the same weight as other, so then you receive the red line. So what I'm gonna tell you today is that you have to take this observation and just throw it away from your observation set. But then for some for analysis, you can use different weights so that you do some manipulations, and then for each observation, you assign some weight of exact this observation and take it to account with some weights. So then how to think about which observation is outlier. So then you do these two models. Firstly, if you don't know that there is an outlier, you estimate your model with all the data, and you will receive the red line. And then what you can do is to check how far away the observation from your model. So you still can see that for most of the data, they are kind of in line with red. And only one outlier is far away. So that, what is this, 5 and 0.2 or 1? So you will have this huge gap. And then we can see that if we take the residuals on the graph, so for green model, most of them lie near 0. And for red model, one of them lie here at -10. So what is your algorithm is to you build the first model, because you cannot build the second one before you drop out the outlier. You make analysis about the residuals. You find one which is far away, or it might be not one, several of them. You throw it away and estimate the second model, and then do the same, unless all your residuals will be somewhere around 0 or distributed kind of the same among each other. So then we already mentioned two tests on previous slide, and here we will go past, for example, of what was that? So it's not written here. It's Bonferroni test. So then let's go back. So you built some statistics based on the regression residuals. So for each observation, so the logic is kind of you check the residual for every observation. S is a standard error for all other observations. So and you can see what if we will think about the outlier, and then the rest of observations are okay, so then S will be low. Then H is some weight which we can use in our test to think about how we want to weight the observation. So then you can think that if you correctly pick the I as a outlier, then S will be small for all other observation, and then your statistics will be larger. So what you're interested in, you build in this epsilon star I for all the observation, and then you find the highest meaning, and this exact observation might be outlier. So this is the logic of the test on the residuals to find the outliers. And yeah, so then you can build some statistics and see how it works, but you will discuss it more precisely later in econometrics. We're not going to talk about it today a lot. So then, yeah, I guess here is some examples. So then you have 33 observation, one parameter, and you find that maximum meaning is 3.4, and that's high. So the general rule is that, yeah, you want to have epsilon star hat estimated lower than or equal than 2. And I guess most of you already got the idea that, yes, if we have some residuals, they are somehow distributed for, so if you have on the line the number of observation, and then you have different residuals, so they are somehow distributed. And if you have one outlier, so that's for one observation, you will have huge residual, then it will increase the variance of your residuals. Yeah, then what you basically want to do, you want to throw out the observation one by one, and then your variance is significantly lower. You throw away exactly this observation. So I think we already talked too much about outliers. Do you have some questions? Fine, let's move to the next slide. Yeah, so and next topic is linear regression with multiple regressors. So and here it's basically the same with only one problem. So I'm not sure if it's on the slide actually. Yeah. Can someone guess what problem now is? Because before you have these all assumptions, then you have only one regressor, and now you have several regressors. Have you heard about the main problem in this setup, which appears now? That's true as well. Actually, I don't know how it works here, but so somewhere here supposed to be the whiteboard. Yeah, you're supposed to see the whiteboard now, yes. So then, okay. Okay, before the model was kind of like this, right? So beta 0 plus beta 1 x I. Yeah. And xi is just one observation. So then, and instead of this, you can think about that xy is beta 0 plus, and then we have vector b and vector x. Yes, and if you remember some mathematics, so that should be b0. And then if these are vectors with let's see, yes, if these are vectors with x 1, 2, 3, 4, 5, 6, and b is a beta 1, beta 2, beta 3. So then you open it, you will have this beta 1 x1 with index I. Sorry for this custom painting. I don't know, my pencil doesn't work. So beta 2 plus x2I. Yeah. Well, and then you open it. So generally, I forgot. It should be multiplication here, right? So, and generally the structure is the same. And then you solving the minimization problem, and you take the first order derivative, and then you have just a sum that doesn't really complicate the analysis to estimate the parameters. I don't know if you already went through it on your exercise sessions or classroom. So then, what is the? Oh, okay, I can choose the color. Nice. So the idea of the model is that you have regressor 1, which is explain how y behaves when you change x 1, but then we have multiple of them. So then you have x2, which affects the change in y. And what you can think with multiple regressors about is then coming back to our example with age and income. Let's say when they're thinking about the education as well, so that somehow they thought that, okay, age is not the one variable which can explain you the income. Maybe education has some other effect as well on your income. And then we would like to ask people about their education as well. So then one question is, if you're just asking them, do you have some higher education or not? That's going to be dummy variable. Or we can ask them about how much years you studied something before you got a job. And then it's going to be 1, 2, 3, 4, and so on years. Yeah, and then what these coefficients will tell you is that fixing the other parameters, for example, taking every one of age 22, which effect on income we will see if we change our education from 3 years to 4 years. So yeah, for example, someone went to school 1 year earlier or later, and they can test how it affects the income generally. Or the other way around, another coefficient should explain you if you fix the years of education. For example, everyone finished bachelor program, and after 4 years of higher education, you can see how your income grow after you finish your education during your career. So like then you are 30, 35, 40, 45. And yeah, what you're going to test with age is if you change the year for age for 1 year, how your income will increase or decrease in the world. And the problem here is then you're going to fix one of them and thinking about the parameter which explain you the effect only of one thing. You don't want to have the interaction between these two regressors. Yeah, because if you change one, if they are somehow depend on each other, so this doesn't make sense. Yes, if for example, if you change the age from, I don't know, if you change the age from how much, 18 for 19, and ask all the participants only in bachelor program, you will increase the age of education by 1 as well. Right, so these regressors will be dependent. Okay, let's go back to our slides. But I guess you understand what I'm talking about. Not give me some feedback. Okay, I press something. What do you mean? And okay. Well, you don't see the slides. Okay, now you see the slides. Should be. Okay, perfect. Yes, that doesn't help exactly, and we will talk about it. So let's go through slides. We already discussed some things. So yes, then we have multiple regressors. So we have a gain constant, and then, for example, two parameters, which define as the slope of dependence. Yes, and the coefficient exactly describes you how your parameter 1 depends on y, then the second parameter is fixed. Yes, so then that's what is written here. So then let's go next. Here is the example of the results. Then you run the regressions. And yeah, what we are studying here, actually know how to read the table such that Konstantin said that you know a little bit, so that yeah, is written the dependent variable, it's income divided by 1000, so this is probably in euro. Then you have constant age, you have gender, and then some other parameters, so that's college. So then gender and college will be the dummy variables, right? Because your gender, if male, then 1, if female, then 0, for example, it's denoted like that. Then college, yes, no as well. So if yes, 1, if 0, then no. And then there is some another regressors. So that's kind of type of the employment. So it's like irregular, part-time, it's officially part-time, and some volunteered training. So then the first model under number 1 describes you what's going on. Then we have just one regressor, age. So that's how income depend on age. So you have some constant, and then adding one age, you will increase your income by how much? 0.03 multiplied by 1000, 30 euro, right? I guess. So, and then the second row, no, second column is the multi-regressor model. Yeah. So, and you can see that now the coefficient for H changed a bit, right? So now then your income explained by other parameters as well. Yes, and probably we can expect some dependence inside the regressors because college and age will interact a bit, I think. Then maybe some type of employment. And what I can see from the table that constant is positive, age positively affect the income in both models. Then males have high income. Those who have a college have high income as well. And then if you are partially employed, then probably you are maybe studying at the same time, so then your income is lower than you are not. Well, okay, and stars describes some level of significance that we're gonna discuss later, more precise on econometrics course probably. So then let's come back to our problem with dependent regressors. And firstly, we start with dummy variables. Yeah, so just as I mentioned, that can be age and college. If you're, male and college. So these are regressors which can be described as 1 and 0. So for example, yes, no questions and something. And how it works in the model. So then you have this dummy variable, you have some additional constant, literally, right? So that if d equals to 1, then you have beta 0 plus beta 1. If d equal to 0, then you have just beta 0 estimated in your model. So that's the logic. So for example, this measure the gap between two different types of observations with two different possibilities. That's how it works. I think it's easy to understand. And then I think next slide is about So it's another example of the model and how the dummy variable gender works. We already observed this on previous slides. Yeah, okay. So then previously on last lecture you discussed how you can test your model if it's good or not, and you remember there were square R measure. And tell me, do you want to have R squared low or high to have a good model? Yes. So, and no, high is no. You want to have R low, right? And high R is a problem. No. Yeah, sorry. and R change from 0 to 1, right? Yeah, a bit. Yeah, there are going to be another statistics later, which works opposite. But yeah, so you want to have R from 0 to 1, and that's how you can measure how your model explain the variables, right? And and now we want to think how we have to deal with R squared in the case of multiple regressors. So firstly, R will increase just because of you add the regressors, because you can get some different effects which are not necessarily explained by exactly these parameters, but because just you have a freedom of 2, for example, variables instead of 1, you can just increase your R because of different structure. And then you have to adjust a bit model, not the model, adjust a bit calculation of R, and taking into account that you increase the number of regressors. And yeah, so what we are going to do is just to do this stuff. So you have yeah, SSR is a TSS minus ESS. And do you remember what does that mean? What is standard R squared? Yes. So then generally you take explained and divide it by total, right? To calculate R squared. But now you do kind of simple stuff. You take 1 minus, and here is inside 1 minus R previously, yes, because if you open SSR, it's going to be, yeah, 1 minus here, 1 minus previous R squared. So if you put this ratio equal to 1, so if k equal 0, then it's going to be the standard R squared. But now you do this simple manipulation to take into account the number of regressors, and then you somehow adjust your R squared. So that's, I don't think you need to know right now something else about the adjusted R squared, but we will gonna use this adjusted R squared to think about how the regressors depend on each other. So you remember, yes, that if R is close to 1, then you have high explanatory power. If R is 0, then it doesn't explain anything in your model. So, and you just need to know that in multiple regressors, you use this adjusted R squared. Yes, and yeah, they already discussed multicollinearity, and this how this problem named. Then your regressors depend on each other. So in this case, you need all the previous assumptions which we made on OLS regression before in case of one regressor. And then we need to check that there is no strong correlation between different regressors. Yes, and I think you can already guess that one example of such a case. Yes, we already discussed one about the age. Then we are thinking about students in bachelor program, and then you increase your age by 1, then you increase your age of education by 1. And the another simple example with this case will be the gender, because if you denote 1 as a male and 0 as a female, or other way around, they are perfectly correlated, because then for one person it's 1, and then it's for those for whom it's not 1, it's 0 by definition, and that's why you have perfect correlation. So you wouldn't include two different regressors as gender male and gender female in the same model. So to see the effect, you're supposed to have only one. So you drop, for example, variable male, and you leave only female and take into account only this. Yes, and what you want to see is how your regressors correlate between each other. And generally, as mentioned here, you don't want to have the correlation higher than 0.9 or lower than minus 0.9. So they're gonna tell you that they explain each other mostly fully. And I talked only about the example that one regressor explained by another, but it can be the case that one regressor explained by all others. So for example, that some combination of 3 different regressors that you have in the model explain another one. So that you cannot really catch this, that as with age or male and female, that you need to drop out one, so that you need to do some tests. And that's why we'll need this error adjusted, R square adjusted. I will talk to you later, but and generally you don't just check the correlation between two of them. You need to see how each of your regression can be explained by other regressors in your model. And we already talked a bit about the dummy variable trap. So here is the example with walkers. So if you want to make some study with walkers, you would not necessarily walkers, but if you ask some participants in your survey or observe some data, and you see there the parameters that if person is occupied or unemployed, so if it's walking or if the person is walking or not, then if you include both parameters in your model, then they're perfectly correlated, because if one is 1, then second is 0, or other way around, right? And then in sum, they will always give you 1. So then you need to kick out one of these regressors. And this is the dummy variable trap, which is normally, it's example with gender, male or female. But there can be another situation. Then you have lots of regressors, and one of them explained by the combination of, and generally it's a linear combination of other regressors. And I'm not sure if, give me a second. Well, I think it will be useful to write for you again on the so if I don't know if I can add another one. How to add another one? No, how? Okay, then you just need to okay, then I have to ask you to imagine that you remember that our model is y equal beta 0 plus beta 1 x1 plus beta 2 x2, and now and then beta 3, beta 4, and now you can rewrite, for example, x1 as a linear combination of x2 and x3, so that x1 is equal, for example, alpha 1 x2 plus alpha 2 x3. So then you can take this and put into our initial model, and then you will have just different parameters, but less regressors. Right? And what we need to do is to write this test for multi-collinearity. So this variance inflation factor to calculate for every parameter, so every regressor. So how it's calculated? So we take 1 divided by 1 minus r squared k. There r squared k is r2 but adjusted. Then you run the regression of your cath regressor on other. I think it's gonna be much better than if I can write it. Okay, now it works. Okay, then we have y equals to, I backdrop the indexes, so beta 0 plus beta 1 x1 plus beta 2 x2 plus, I think 3 of them will be enough. And we are assuming that x1 can be explained by x2 and x3. So what we actually do in our model, we write down the different regression. Yes, that x1 is equal to alpha 0 plus alpha 1 x2 plus alpha 2 x3. So yes, so they write this regression. Then we got our estimators. Yes, alpha 1 hat, alpha 2 hat. So and for this exact regression, we can now calculate r squared adjusted, because we have again multiple variables here, multiple regressors. Yes, and what we want to see in this regression, we want to see that r squared now will be low or high. So if x1 is well described by this x2 and x3, then we can substitute x1 by all this stuff here. What we actually can do then is, so we can take this model and put it inside here. right? So, and yeah, in our initial regression, we just will delete x1 from the analysis if they are explained. So if R here in our second regression is high, which means that x1 can be well explained by x2 and x3, and R is high, then you dropped this regressor from the analysis because you just don't need. You can explain everything by other regressors. So how to go back to? Okay, let's go back to our slides. So then R squared is high, then this index is high as well. So the IF, right? Because difference is low. Then VIF is high. So then you have high VIF for some regressor. You want to drop out this regressor. I guess it's clear. Okay, yeah, and then you have VIF equals to 1, then it's okay. There is no correlation between this regressor and other regressors, and you can for sure leave a regressor in the analysis. So, and how you should think about this: if VIF is higher than 10, then it's a strong correlation, and you have to drop out this regressor. If it's more than 4, you have multicollinearity, but you still can leave these regressors in your analysis, and maybe you just need to drop out some different regressors, so you have to repeat all this test for every regressor, and it's going to be better. Yeah, but generally what you do, you run VIF for all the regressors, drop out the one with highest meaning, and repeat this test again. So then that's how we deal with multicollinearity. And so then we have to talk a bit about the hypothesis testing. So I will just briefly mention that with hypothesis, you works kind of the same. So then you have to clearly state the hypothesis to understand what's going on and what is the other opportunity. Yes, for example, if your H0 is that yes, all coefficients are with exact sum meaning, then you have some number of these equalities here as in the hypothesis. And I don't know why it's denoted here by number R, but it doesn't matter. So the alternative hypothesis will be that if at least one of these conditions are not met, which means that some of them are 0, for example, or not, then it's violation of hypothesis. So there is another example that you can test as well, hypothesis that you have two regressors that coefficients are equal to each other or not equal. So you just need to be a bit careful here how you formulate your hypothesis. So yeah, and then to test hypothesis, you use F statistics. Yes, it's similar to T statistics, which you discussed before with a single regressor model. but now then it's just for car regressors. But if you drop down to one regressors, then you will come back to G statistics. Yes, okay, and that's a bit about hypothesis. And I think yeah, so here is some example that F statistics gives you again some percentile, and you can do pretty the same as with T statistics, but I'm not sure if you're gonna derive it by hands in classroom. I think you will just ask to know how to use it in Stata or R. So you just need to know the name of the test and what's going on. So as I remember, you have a test in 5 minutes, right? Already 4 minutes. Okay, then just I will be and discuss a bit more. Yeah, it's one more slide about hypothesis. So then you're making these tests, then coefficients are equal to each other. Well, and it sometimes doesn't work nicely with F statistics. You slightly transform your model to another one, and you can just test it with hypothesis that gamma is equal to 0. Yeah, because the other part is if gamma equal to 0, then you end up with the same model, but with B2, B2 instead of B1, B2. And yeah, that's some small tricks in econometrics. I think you're for sure going to discuss on Excel sessions. Yeah, and another big topic is nonlinearity. And yeah, we have 3 minutes, and I will slightly talk about this. Yeah, before we talked only about linear regressors, and yes, but sometimes your data described a bit differently. I think the next slide, you can see the data looks like quadratic, for example. And if you run the linear regression, you have a lot of outliers, for example, or generally what's going on, you picked your model incorrectly. So then you're going to think about quadratic, logarithmic, or another model. Generally, it looks like you have some function. And the meaning is that now instead of coefficients, you have function, and then inside you have some dependence as well. So what you need to do basically is to guess the type of the function, and then you could do the same regression as before. Yes, and the closest example is a quadratic model. Then you have xi and xi squared. So then you estimate these parameters in OLS. Then, and you can see that in quadratic, the model fits the data much better. Oh, and a bit more about meaning of such estimation is that if you slightly change your one parameter, one regressor, x1, leaving the rest parameters fixed here, yes, and that's the difference in the function if you change a bit x1. How this responds to change into your dependent variable, right? It's basically the logic is the same, but now you have some function instead of linear function. You can have different form. So, and here's some example. And there are, have some T and F statistic you can use as well. And then one more important stuff I want to tell you today is that in nonlinear models, what is often used is linear model or logarithmic model, sorry. And yeah, logarithm just kind of the same as the percentage respond to the change in the argument. So if you change the your regressor by 1%, you can see for how much percent you will change the dependent variable. Yeah. So then good luck on test. I will ask you later to fill one questionnaire about how I did the lecture. It's kind of important for me, but I send you on Telegram. Then thank you for participation. Don't forget to go through slides after the lecture, and good luck on the test. Bye.